Okay, welcome back, and today we're going to start binomial probability. And first thing we're going to talk about is the binomial experiment. Okay, so what is a binomial experiment? It's an experiment, it's a probability experiment where certain conditions have to be satisfied. There are 5 conditions. Okay, now they list 3, but you can actually break these up into 5. I always list 5. The same experiment is repeated for a fixed number of times. So there's a fixed number of trials. Each time you do an experiment, that's called a trial. So there's a fixed number of trials. There are only 2 possible outcomes for each replication of the experiment, which means that it's either going to be a success or a failure. So there are only 2 possible outcomes. Okay, that's going to be, and we also call these Bernoulli trials. Okay, so there's only 2 possible outcomes. So that's another one. The repeated trials are independent of each other. Okay, so we've got repeated independent trials, which means the outcome of one trial does not affect the outcome of the previous trials, or definitely the outcomes of the next trial. Okay. Also, number 4, the fourth condition is that the probabilities are consistent. The probability of getting a successful outcome on a trial stays the same for each trial. So those are the 4 conditions, but then the random variable has to be defined a certain way. And so we have to be counting the number of successes out of the n trials. Okay, so there's a fixed number of trials, we call that n. We detect that as a sample size. So if there are n trials, and we want to know how many successes there are out of those fixed number of n trials. That's a binomial experiment. Now, binomial probability, if that's the case, if our experiment falls into this category, then probabilities of having a certain outcome or a certain number of successes is very easy to calculate. In fact, it's just based on this formula. We figure out how many different ways, how many combinations, what's the combinations, right? The number of ways of getting X successes out of n trials. That's a combination. We don't care about the order. All we care about is how many different ways can we get X successes out of n trials. And then what we're going to do is we're going to take the number of successes, right? And since they're independent of each other, it's the multiplication rule. So we take the probability of success, since it's the same, and we multiply it by itself. How many times? Well, the number of successes, and that's where we get p to the x. And then likewise, we take 1 minus p, or sometimes I also write this as q. Okay. In fact, I will typically just write this. Let me do it this way. This 1 minus p is just q. Okay, so this can be q to the n minus x, because if there's x successes, then the rest of the trials, n minus x, has to be failures, which is 1 minus p, or what I call q. Okay, so this is the binomial formula for probability, and this gives us the probability of having exactly x successes out of n trials. Okay, and so let's see here. So now, remember Pascal's triangle. I mentioned this in class. So the combinations, this basically follows from the combinations, right? So this would be n equals 0. So this would be, corresponds to if n equals 0. Okay, so this would be n, oops, n choose 0. Okay, or in this case, if n is 0, it's 0 choose 0, which is still 1, right? So this is going to be 1. That's where the 1 comes from. And then, of course, this is, if we have 1, well, there's 1 choose 0, which is 1. Gosh darn it. And then there's also 1 choose 1, which is also 1. So you get 1, 1. And so each one of these numbers, so this would be n equals 1, n equals 2, n equals 3, n equals 4, and n equals 5, and it all gives you all of the different combinations. So this would be 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 1. And so I saw this I told you guys this in class, but I'll bears repeating. Okay, so this is what we're known as Pascal's triangle. You may have seen this when you took college algebra, either in high school or in college, and when you had to expand out this. So you had this polynomial, and you had, let's say, x plus y to the n. Well, if you expand this out, for example, if you take 3, right, just to keep it simple, so what you know is if you know the Pascal triangle and you know the pattern for expanding these out, then you get x to the third, plus x squared y, and then you get x xy squared, and then there we go. Now, notice how the pattern n equals 3, this is 2, y is 0, so there's no y, so it's 2 and, or excuse me, 3, this is 3, 3 and 0, then you get 2 and 1, 1 and 2, and 0 and 3. So they all add up to 3. And now the coefficients, though, correspond to the combinations for n equals 3. So that would be this one here. Okay, so notice that 3 choose 0 is 1, so this would be 1. And then 3 choose 1 is 3, so this would be 3. And then 3 choose 2 is 3. And then 3 choose 3 is 1. And there you go. So just to give you a little background of where these come from and why this is powerful as far as the combinations go. Okay, so, oops, I did not want to do that. Hold on. So now let's do a couple of examples. Hold on. Okay, so let's see here. Okay, so we know, and it says a recent survey found that 59% of college students attend more and more institutions during their college career. Suppose a sample of 6 students is chosen, assuming that each student's college attendance pattern is independent of the others. Find the probability of each of the following. So let's take this one. Exactly 3 of the 6 students attend more than one institution. So the first thing we ask ourselves is what? Well, is this a binomial probability? Or a binomial experiment. It sounds like one, but let's go through the conditions. Okay, so 1, is there a fixed number of trials? Yes, because each student is considered a trial, right? You randomly select 6 students from the population, and so each student's choices are going to be different. Okay, well, are going to be independent of the other students' choices, right? And there's only 6 students, so each student is a trial, so there's only a fixed number of trials. The probability of their choice is independent of the other one. It's also fixed because based on the survey, 59% of college students attend more than one institution during their college career. So either they're going to choose more than one or they're not. Okay? So there's only two possible outcomes for each choice. Either they're going to end up going to more than one institution or they're not. Okay? Each student's, whether a student goes to more than one institution or not, is independent of whether another student does that or not. So that's independence. We're only choosing 6 students, right? And we know from the survey that the probability that a student goes to more than one institution in their career, academic career, is the same, 0.59. And so, and we're interested in what? The number of students who attend more than one institution in their academic career, which means that we're counting the number of successes where, in this case, we're defining a success as whether they attend more than one institution in their academic career path. Okay, so again, now keep in mind that a quote-unquote success may not be a positive thing. Okay, it's just what it is, whatever it's defined, whatever we're counting. In this case, we're counting the number of students who attend more than one educational institution. Okay, so in this case here, it is a binomial experiment, so which means we can use our binomial formula. And so we're going to find the probability that x, where x is counting the number of students out of the 6 who attend more than one institution in their career, their academic career. So this is going to be x equals 3. And so this is going to be what? This is going to be what? Out of the 6, we're choosing 3. So how many different ways can I get 3 successes out of 6? And then we're going to multiply by the probability of a success, which in this case is 0.59. And so how many successes are we going to have? 3. And then we're going to multiply that by the probability of failure, which means that they don't go to more than one college. So that's going to be what? 0.41, because it's the complement, right? Successes and failures are complement of each other. Okay, and then that's going to be raised to what? That's also going to be raised to the 3rd power because it's 6 failures. If you have 3 successes, then the other 3 had to be failures. And so now all we do is plug this into our calculator. And so let's figure this out. So we're going to plug this in. Okay, so 6 choose 3 is going to be 6 times okay, so we're going to have 0.59 raised to the 3rd power. That's going to give us 0.2054. Now I'm rounding here, but I would not round in your calculator, but just for presentation purposes. And then 0.41 raised to the 3rd power, 0.0689. Okay, and so what do we get? We're going to get Hold on one second. I know you guys are probably faster than me. 0.2831. 0.2831. So the probability that 3 out of the 6 randomly selected college students will attend more than one college during their academic career is 0.2831. And that's the answer. Okay. So now this is a lot faster than trying to figure out the combinations and adding them up like we did before using the concepts and principles from the last section. We could do that, but if we know that it's a binomial experiment, then we can use the binomial formula, and it's just plug and chug and much faster and easier than using the techniques from the previous section. So other than that, that's really all there is to this section. So next time we're going to look at probability distributions, and we're also going to talk about the expected value of a distribution. So next time, be prepared. We're going to do that. And so until then, make sure you do the examples. There are plenty of examples that I have not gone over in the textbook. Make sure you go over those examples. Try them out by yourself. Do the try-its, the ones that the other examples that don't have the solutions. Try to do those. If you get stuck, ask me about them. Either email me or bring those to class, and we'll work them out together. And so make sure you bring your questions and be ready to work and practice in class. Until then, have a great day. Bye-bye.